Yes, there is a potential for the primary overcurrent protection devices to trip on inrush current. Inrush current is a brief surge of current that occurs when a transformer is first energized. This surge can be several times the normal operating current of the transformer. For the 100 kV transformer, the inrush current can be estimated as inrush current equals 25 times transformer kilovolt-amps equals 25 times 100 equals 2500 amps. For the 150 kV transformer, the inrush current can be estimated as inrush current equals 25 times transformer kilovolt-amps equals 25 times 150 equals 3750 amps. The overcurrent protection devices that are currently installed are rated for 225 amps. This is significantly lower than the estimated inrush current for both transformers. Therefore, it is likely that the overcurrent protection devices will trip on inrush current. Upgrading the overcurrent protection devices to a higher rating will be necessary to prevent them from tripping on inrush current. The new overcurrent protection devices should be rated for at least twice the estimated inrush current. When a transformer is initially energized, it experiences a phenomenon known as inrush current. This is a high-magnitude transient current that can be significantly larger than the transformer's normal operating current. Several factors contribute to the occurrence of inrush current, including the core's residual flux, the point on the voltage wave at which the transformer is energized, and the transformer's impedance. The magnitude and duration of the inrush current depend on the transformer's design, size, and the characteristics of the source impedance. Inrush current can cause various problems, such as voltage dips, equipment malfunction, and premature aging of transformer components. In extreme cases, it can even lead to the failure of protective devices or the transformer itself. Therefore, it is essential to understand and mitigate the effects of inrush current. Several methods can be employed to reduce inrush current, including using pre-insertion resistors, controlled switching devices, and specialized transformer designs. Pre-insertion resistors are temporary resistors inserted in the circuit during energization to limit the initial current surge. Controlled switching devices use sophisticated algorithms to energize the transformer at a specific point on the voltage wave, minimizing the inrush current. Specialized transformer designs incorporate features that reduce the core's residual flux and improve the transformer's impedance characteristics. To prevent nuisance tripping of overcurrent protection devices due to inrush current, it is crucial to select appropriate devices with sufficient time delay characteristics. These devices should be able to withstand the short-duration inrush current without tripping, while still providing adequate protection against sustained overloads and faults. Coordination studies should be performed to ensure that the overcurrent protection devices are properly coordinated with the transformer's thermal withstand capability. This will prevent the transformer from being subjected to excessive thermal stress during inrush conditions. In addition to selecting appropriate overcurrent protection devices, it is also important to consider the transformer's insulation system. Inrush current can generate high-frequency voltage transients that can stress the transformer's insulation. Therefore, the transformer should be designed with adequate insulation margins to withstand these transients. Regular maintenance and testing of transformers can help identify potential problems related to inrush current. Insulation resistance tests, turns ratio tests, and excitation current tests can provide valuable information about the transformer's condition and its ability to withstand inrush current. If any abnormalities are detected, further investigation should be conducted to determine the cause and implement appropriate corrective actions. Upgrading the primary overcurrent protection device for the 100 kV transformer to a 3-pole 500 amps thermal magnetic primary overcurrent protection device is recommended. Likewise, upgrading the primary overcurrent protection device for the 150 kV transformer to a 3-pole 750 amps thermal magnetic primary overcurrent protection device is also recommended. The potential for overcurrent protection devices tripping on inrush current is a common concern when energizing transformers. Inrush current, as previously described, is a transient phenomenon characterized by a high-magnitude current surge that occurs during the initial energization of a transformer. This surge can be several times the transformer's rated current and can last for a few milliseconds to several cycles. The magnitude and duration of inrush current depend on various factors, including the transformer's size, design, core material, and the point on the voltage waveform at which the transformer is energized. When a transformer is energized, the magnetic core is initially unmagnetized. As the voltage is applied, a large magnetizing current flows to establish the magnetic flux in the core. This magnetizing current is superimposed on the normal load current, resulting in a high inrush current. The inrush current waveform is typically asymmetrical, with a large peak on one side of the zero current line. This asymmetry is due to the core's residual flux, which is the magnetic flux that remains in the core after the transformer is energized. The residual flux can either aid or oppose the establishment of the new magnetic flux, depending on its polarity and magnitude. If the residual flux aids the establishment of the new magnetic flux, the inrush current will be higher. Conversely, if the residual flux opposes the establishment of the new magnetic flux, the inrush current will be lower. The point on the voltage waveform at which the transformer is energized also affects the magnitude of the inrush current. If the transformer is energized at the voltage peak, the inrush current will be lower. However, if the transformer is energized at the voltage zero crossing, the inrush current will be higher. This is because the voltage zero crossing corresponds to the maximum rate of change of voltage, which induces a higher magnetizing current. The transformer's impedance also plays a role in determining the magnitude of the inrush current. A lower impedance transformer will have a higher inrush current, while a higher impedance transformer will have a lower inrush current. The transformer's impedance is determined by its design and construction, including the number of turns in the windings, the size of the core, and the type of core material. To mitigate the potential for overcurrent protection devices tripping on inrush current, several strategies can be employed. Firstly, the overcurrent protection devices should be selected with appropriate time delay characteristics. These devices should be able to withstand the short duration inrush current without tripping, while still providing adequate protection against sustained overloads and faults. Secondly, pre-insertion resistors can be used to limit the inrush current. These resistors are temporarily inserted in the circuit during energization and then bypassed after a short period. The pre-insertion resistors reduce the initial current surge, preventing the overcurrent protection devices from tripping. Thirdly, controlled switching devices can be used to energize the transformer at a specific point on the voltage waveform, minimizing the inrush current. These devices use sophisticated algorithms to determine the optimal switching point and can significantly reduce the magnitude of the inrush current. Fourthly, specialized transformer designs can be used to reduce the core's residual flux and improve the transformer's impedance characteristics. These designs incorporate features such as gapped cores and amorphous core materials, which reduce the residual flux and lower the inrush current. In addition to these strategies, it is also important to consider the transformer's operating conditions. The inrush current can be affected by factors such as the transformer's load, the system voltage, and the ambient temperature. Therefore, these factors should be taken into account when selecting and coordinating the overcurrent protection devices. In summary, the potential for overcurrent protection devices tripping on inrush current is a significant consideration when energizing transformers. By understanding the factors that contribute to inrush current and implementing appropriate mitigation strategies, it is possible to prevent nuisance tripping and ensure the reliable operation of the transformer. For the 100 kilovolt-amps transformer, the inrush current can be estimated as inrush current equals 25 times transformer kilovolt-amps equals 25 times 100 equals 2500 amps. The primary current is calculated by taking the kilovolt-amps divided by the primary voltage. In this instance, that is 100,000 volt-amps divided by 480 volts, which is about 208.33 amps. The inrush is therefore 2500 divided by 208.33, giving us an inrush of approximately 12 times the primary current. For the 150 kilovolt-amps transformer, the inrush current can be estimated as inrush current equals 25 times transformer kilovolt-amps equals 25 times 150 equals 3750 amps. The primary current is calculated by taking the kilovolt-amps divided by the primary voltage. In this instance, that is 150,000 volt-amps divided by 480 volts, which is about 312.5 amps. The inrush is therefore 3750 divided by 312.5, giving us an inrush of approximately 12 times the primary current. Firstly, consider thermal magnetic circuit breakers, which are commonly used for transformer protection. These breakers have two tripping mechanisms. Thermal element responds to overload currents, providing inverse time tripping characteristics. Magnetic element responds instantaneously to high fault currents. The inrush current is a high magnitude, short duration current. The magnetic trip element can trip if the inrush current exceeds its setting. Secondly, to prevent nuisance tripping, choose a breaker with a higher magnetic trip setting. Standard rule of thumb is to select a breaker with a magnetic trip setting above the inrush current. Thirdly, consider using a circuit breaker specifically designed for transformer protection. These breakers have special features to handle inrush currents, such as high magnetic trip settings or time delay functions. Fourthly, fuses also are used for transformer protection. Fuses have inverse time tripping characteristics, meaning they trip faster for high currents. The inrush current can cause a fuse to blow if it exceeds the fuse's melting time characteristic. Fifthly, to prevent nuisance blowing, choose a fuse with a higher amp rating. Standard recommendation is to select a fuse with a continuous current rating at least 150% of the transformer's primary current. Sixthly, consider using a time delay fuse, also known as a dual element fuse. These fuses have a built-in time delay that allows them to withstand short duration inrush currents without blowing. Seventhly, protective relays are used for transformer protection in more sophisticated applications. These relays can be programmed with various protection functions, including overcurrent, overvoltage, and differential protection. Eighthly, differential protection is a sensitive protection scheme that detects internal faults within the transformer. It compares the currents entering and leaving the transformer. If there is a significant difference, it indicates a fault and trips the breaker. Ninthly, relays can be programmed to ride through inrush currents by using harmonic restraint. Harmonic restraint desensitizes the relay during inrush conditions by detecting the presence of second harmonic currents, which are characteristic of inrush. Tenthly, consider using a solid-state relay with advanced inrush current detection capabilities. These relays can distinguish between inrush currents and fault currents, preventing nuisance tripping. Finally, it is important to coordinate the transformer's protection with the upstream and downstream protection devices. This ensures that the fault is cleared by the closest device to the fault, minimizing the impact on the system. Recommendation: upgrade the primary overcurrent protection device for the 100 kilovolt-amps transformer to a 3-pole 500 amps thermal magnetic primary overcurrent protection device. Upgrade the primary overcurrent protection device for the 150 kilovolt-amps transformer to a 3-pole 750 amps thermal magnetic primary overcurrent protection device.